Okay, now this is recording. I was saying this is just a recap of the lecture. We have gear 1. Let's call this gear 1. And let's call this gear 2. Gear 1 is rotating with an angular velocity omega 1. And gear 2 is rotating with an angular velocity of omega 2, but we know exactly what is omega 1. So we also now have complete geometry information. So we know that this is the radius of gear 1, and this is the radius of gear 2. But we also know that the kinematic relationship is that this point here, which is the only point in common between these two gears, has a single speed. So the velocity of this point is the same if you look at this gear or if you look at this gear. Now, how do you explicitate the velocity of a point? Remember, kinematic relationship for in first year, remember when we did rotational motion, any point that is rotating around a fixed point has a velocity equal to omega, which is the angular velocity of the entire body, times the distance at which that point sits with respect to the fixed point. Now the fixed point here is O1, the fixed point here is O2. So this is omega 1 times the distance between O1 and P, which is the radius of the first gear. This is what we know. And this is, of course, it's a cross product. But we can also write the same relationship for the second gear. Do you agree with me? So this, if I look at the first gear, I get this. If you look at the second gear, I get this. And so I can find what's happening to omega 2. Omega 2 is just R1, sorry, is R1 over R2 times omega 1. Okay? Now, I don't like to use this. What I like to use is the transmission ratio, which is the ratio of the omegas, right? So we know that omega 2 goes in this direction. And it must be in that direction. So you know that if you have externally meshing gears, as you have it here, you have a transmission ratio. You know that omega 2 is equal and opposite to omega 1. All right? Now what I want to introduce is what we call transmission ratio, which is just omega 2 divided by omega 1. So I can get rid of this. In fact, let me rewrite this in a better way. I'm going to say that eta 1, 2 is omega 1 over omega 2, which is minus R2 over R1. Do you agree with me? This is exactly the same equation rearranged, and then I introduced something that I call transmission ratio. This one is what we call transmission ratio. Okay? So this is a negative number because the gears are meshing externally. Now we might have a positive number if the gears are meshing internally. So what you might have is a situation like this. You have a large gear and you have a smaller gear, and they mesh like this. Okay? So if they mesh in this way, this is pinned and this is pinned, they mesh in this way, the velocity of this point, say, it's the same, Vp. So if this is going in this direction, omega 1, of course, this is also going in this direction, omega 2. See, now in this case, for internally meshing gears, what you have is that omega 1 and omega 2 have the same sign. So negative, so this can be, let's make it like this, negative or positive, R1, R2 over R1, positive for externally meshing gears, and negative for internally meshing gears. Okay. I think that's all you need. Let's have a quick example, very quick. What happens if I have a gear train? This is called a simple gear train because you have 3 gears. And you are driving one. This looks like Mickey Mouse. I don't want the Disney lawyers to sue me. So if I have this, and I rotate this omega-1 in this direction, how does omega-2 rotate? Well, in this direction. Okay, so this is counterclockwise, so this is clockwise. And so that omega-3 is? Okay. Sorry. The other way. Okay, good. Let's look at the transmission ratio. Now, this is the input gear in, and this is the output gear out. So what I want here is eta 1,3. Okay, eta 1,3 is omega-1 as I defined it. Eta 1,2 is omega-1 over omega-2. So eta 1,3, so output, input, and output is omega-1 over omega-3. Okay, how do I do this? The problem is, look at this. These gear don't mesh. Omega-1 and omega-3 don't mesh. So I can't say it's this, because this relationship is true only if they are in contact, because we are making use of this VP. All right? Agreed? In this case, they have no point in common, but they share something via omega-2. So I can turn this into a ratio that says, well, omega-1 over omega-3 is the same as omega-1 over omega-2 times omega-2 over omega-3. Do you agree with me? It's just the same thing, because omega-2 and omega-2 go away. And now these two, look at this. This one, omega-1 and 2, they do mesh. And omega-2 and 3, they do mesh. And so now I can do this. So this is omega-1 over omega-2 is R2 divided R1, negative because they are externally meshed. This is the other way around. Why didn't you stop me? This is internal mesh, and this is external mesh. Okay, so it's negative because they are externally meshing. So this is minus R2 over R1 times minus R3 over R2. And so in total, the transmission ratio of this gear train is R3 over R1 positive. See? So the effect of having a gear in the middle, it's just to change the direction of rotation. That's the idea. And that's why we tend to make this gear as small as possible, because we don't, and it's useless. Almost useless. It's useful because you want both these shafts to turn in the same direction. So it is useful in this sense, but it's not useful to change anything. So you try to make it as small as possible. In Italy, we call this gear, we call it galoppino or ruota folle, which is like a full wheel, because it doesn't do anything. It's called the full wheel, the full gear. All right, that's almost it. One other thing is that you know what a module is. Do you know what a module is? The module of a gear. What is that?
Pitch diameter divided by number of feet.
Yeah, but what is that?
Just like constant for the system.
Second?
Just like a constant for the whole system.
Yeah, why?
Only gears with the same module mesh.
I mean, the gears just fit each other.
So the fact is, when you want meshing gears, you must make sure that every tooth matches with a hollow part, okay? So that means you must have, if you have the same gears, the same dimensions, they must have the same number of teeth, okay? But if one gear is larger, you must have more teeth in a certain ratio. That ratio is how many teeth you have per diameter length, which is just the same how many teeth you need in the circumference. Now, of course, circumference, you teach me, is just 2 pi times r. So pi goes away, and it becomes 2r, which is d over t. Okay, so what you want is how many teeth you have per arc. That must be constant. How many teeth per arc, per angle. So for the full circumference here, you need a certain number of teeth. And so what you need is a module. Let me call it here module. M, which it's 2 pi r divided by t, but of course pi can just go away. We don't care about pi. So it's d divided by t. Yes?
Are there any scenarios where you'd want to change the module?
The module, yes. So you want to change the module because the module is directly responsible for the height of the tooth as well and the thickness of the tooth as well. So if you have very heavy gear meshing, you want to make the tooth thicker, because if it's too thin, it will break. Okay, so it's very easy to break it. So we have standard modules.
And would you change the module by introducing a compound gear?
No, not necessarily, but yes, you can do that, but not necessarily. Yeah. If they are different module, as I see a chat, I see someone in chat asking, if they are a different module, that means at some point you will clash teeth, or you will encounter two hollow parts. Okay, so you are just not making full use of the gear or breaking the system entirely. So that they must have, meshing gears must have the same module, must have the same number of teeth around a certain circumference. All right. So d over t, that means what are the units of module?
Meter.
Yeah, so it's a length divided by a number. It's just millimeters. That's what we use generally, so it's a length. Okay, but let's look at this. So this is also 2r over t. Agreed? Agreed. So that means if the gears all share the same module, I can say that I can find the radius of the gears by knowing the module and the number of teeth. And remember what I told you, this is the transmission ratio. So I can say that the transmission ratio is also mt2 divided by 2 divided by mt1 divided by 2. Of course, m divided by 2 and m divided by 2 go away. So I can say that the transmission ratio is omega 1 over omega 2. This is the definition. But this is also equal to minus or plus R2 over R1, which is also equal to minus or plus T2 divided by T1. Okay? If the gears have the same module. Yes?
For the module example that you're doing, are the radius?
R is the radius, yes.
And for the example looking for the revolution, what's the story radius?
Say again, sorry?
For the other example you did before, which is
Yeah.
the radius or the revolution.
No, it's just radius. It's always radius, see? R1, R2, yeah.
Oh, yeah.
All right, good. So this is also radius, what I'm saying here. This is R1, this is R2. Okay? Okay, that's it. That's all you need, really, all you need. This is the takeaway. And we used definitions and everything just to make sure that everything checks out. Now let's solve question 1, which is an epicyclic gear train. Now, what is the difference between an epicyclic gear train and a compound gear train? Epicyclic gear trains have not all axes of the gears are fixed. If all the axes are fixed and they rotate, that's a compound gear train. If they move around in some way, that's an epicyclic gear train. Since they move generally all around a sun, it's epicyclic because the motion of a single point on a gear follows the epicyclic curve. That's why it's called epicyclic gear train. Now, you must be aware on how to recognize the parts. Now, you will have this kind of thing at the exam. At the exam, this is given. And you should be able to recognize the suns, which are the gears that do not revolve. They only rotate. The planet, which revolves around the sun. And if you have a ring gear or not. Now, the planets are carried around by a carrier. It's called the carrier arm because there's an arm that carries the planets around. Okay, now let's look at this. This is a section of the gears, section of the gearbox. And this is the line representation. As you can see, this looks very much like this. Now, these ones, this is a gear. Oh, this is a gear. This is the tooth. So this is gear with teeth. And this is the shaft the gear is mounted on. Okay, so that's how you represent a gear in a line diagram. So as you can see, this one is another gear. It's called gear 2. Now these two mesh with another gear, which is this one. Now this is a bit complicated because it's a planetary body. So what you have is a dumbbell, basically. It's a shaft with two gears. That's what you have. One is larger, one is smaller. And this dumbbell has a hollow shaft. In the hollow shaft, so as you can see, inside the hollow shaft, you have the carrier arm. Okay? So the carrier arm goes inside the planetary gear and carries it around the suns. And the last thing you have here is the ring. It's the ring gear, which, as you can see, has internal teeth. Can you see it? The teeth are inside. Looks like this. Looks like this. Okay, looks like this, like a claw, and the gear mesh inside this. Okay. So, what we can say about this? We have body 5. What is this? Is it a sun? Yeah. Okay. See, it doesn't go anywhere. It stays there, and something revolves around it. It is a sun gear. What about 2? What is it? Second? Is it a planet, a sun, or car? It's another sun, like in Star Wars. You have 2 suns. What about body 3, this green one? That's a planet. How do you recognize a planet? It's easy because the planet always goes around suns, so it's never in the center of the diagram, otherwise it would be a sun, and it's always engaged by the carrier arm. Okay? So 3 is a planet. I like to call it planetary body because it's not 1 gear, it's 2 gears. It's a dumbbell with 2 gears. Make sure you understand this. It's not 1 gear, it's 2. See, you have teeth on this side and teeth on this side. What is 4? There's a ring. And finally, what is 6? It's the carrier arm. The carrier arm has its own angular velocity. It's the only thing that is not a gear. It's the only thing that has no teeth, but still rotates. Okay, it's an arm that rotates around. So it has its own angular speed. All right. Now that we have these, are all planets hollow? Yes and no. Yes, because generally they are, but there are some instances in which they are not. It depends on the design. Let me show you this case. So in this case here, if you look at the planet in this case is 4, and the carrier arm is hollow. See, the arm is hollow, and the planet goes inside the arm. Okay, but this is the only example that you have here. In all the other examples, see the planetary body is hollow and the carrier arm fits inside. See, hollow, and this fits inside. Okay, good. Now let's make a quick fact check. Let's look at this one. How many suns you have in this figure? 1. Which one is that? 5. How many planets? 1. Okay, which one is that? 3. That means the carrier arm is 2. Okay, what's 4? That's a ring. Let's look here. How many ring gears you have here in figure 3? How many ring gears? None. There are no ring gears. There is no ring. There are no internal meshing gears. Okay? So how many planets you have here? Is it 1 or 2? It's 1 planetary body with 2 gears. Okay. Okay. So and they are saying they're all dumbbell-like. No, they're not all dumbbell-like. Look at this. This is a planet gear 3, which is just a single. It's a planetary body with a single gear. There's a single gear, and they can have 1, 2, 3, as many as you want, and you can have multiple planets as well going around. Okay, very good. Now we can start. Yes.
What do you mean by dumbbell?
Dumbbell is it's the dumbbell.
Oh, like the gym. Oh,
Yeah,
okay.
it's actually a gym dumbbell.
Oh, yeah.
I have one question.
Yes.
So on the left example, it
Yeah.
seems like symmetric, right? Because there's like another gear at the bottom, like
Yeah.
5.
Yeah.
Why is it not in the diagram?
Because this is a section. If you have 3 planets at 120 degrees, you can only show 1. Okay.
No.
Okay. So it depends on how you section it. All right. These go around. All right. Good. Yeah.
But it's just like this, like the ones on top.
Exactly.
Like that.
And you can have 2 more at 1. Yeah. Exactly.
So that just shows one of them.
Exactly. It only shows 1 because it doesn't need to show you.
So if it works with one, it works with three.
Exactly. But it must. The question must be. The question must be explicit on how many you are. See, question 5 says there are 3 sets of planet wheels. Okay. So question 5 says explicitly there are 3 sets of planet wheels. Okay. Let's start with question 1. Figure 1, which is what we just had here. Yeah, this one. Figure 1. It's an accelerator gear train together with a line diagram representation. All the gear wheels have the same module. Very good. The compound wheel 3, see, compound wheel, that's what I call the dumbbell because it looks like a dumbbell. Compound wheel 3 rotates on a spindle fixed to the spider 6. It's called a spider because the carrier arm, if it has 3 arms, looks like a spider. Okay, that's the idea. Huh? But spiders have 8. But you get the idea. Body 6 is the output shaft, and body 2 is the input shaft. This is extremely important. Extremely important. So body 6 is the input shaft. 6 is the input. Let me write it down here. 6 input.
6 is the output.
Oh, 6. Sorry. Thank you. 6 is the output. So what's the input? 2. So the sun is the input. Now, one thing I didn't tell you is that epicyclic gear trains are 2 degrees of freedom mechanisms. That means you can't have one input, one output. You can have 2 inputs, 1 output, 1 input, 2 outputs, and you can have 1 input, 1 output, and 1 fix. Okay? And if you change the configuration, so if you fix one, you have 1 output. If you fix the other, you have another output. Okay, so you can, that's why you have automatic gear meshing, automatic gears with epicyclic gear trains. If you have a train of these, every time you have to switch gear, you fix a different component. That's the idea. Okay, so you get a different gear ratio out of it. So that's very useful. You just have this in cascade, and every time you fix one component of each. And this can be done automatically by having, I don't know, by using centrifugal force. Okay, so you have some sets of brakes that expand if you reach a certain speed, and as they expand, they lock the ring gear, say. And so the next one gives you a different gear ratio. So if you increase the speed, the other one locks, and so on and so forth. So it's all automatic. Determine the teeth numbers T2 and T4 if T3 is 25 and capital T3 is 30. Now let's look at this. We want to determine T2 and T4.
What's capital T?
Yeah, that's what I'm going to explain now. So small t3 and capital T3. Small t3 is 25. Capital T3 is 30. And small t5 is 40. Now let's look at the picture. Look at body 3. Body 3, as we said, has 2 gears. That means they are not the same gear. One is larger, one is smaller. Now the smaller gear is small t3. The larger gear is capital T3. Okay, so it's just saying that the number of teeth on this dumbbell are not the same. So we have 25 on this side and 30 on this side. All right? Okay. Now, we want to find, since we know that all the modules are the same, we want to find what must be the number of teeth in gear 2 and what must be the number of teeth in the ring gear 4. How do we do that? Well, this is the geometry. So we don't know about number of teeth, but we know about the radii, because they must fit all together. If I make it too large, it doesn't fit. So what I do is, what I do is go here and say, let's start from, this is my 0. Okay, this is my 0. So the radius of gear 2 gets me here, all right? Radius of gear 2 gets me here, R2. If I add the radius of small gear 3, this was in green, let's call this small R3 because it's the small gear of body 3. Now I am on this shaft, all right? If I add the larger radius, now I'm here. If I add the larger radius, R3, I get onto the radius of 4. Do you agree with me that this is exactly the radius of 4?
Yes.
So I can write an equation that says R2 plus small r3 plus capital R3 equal R4. Agreed? That's my first equation. I need 2 because I have 2 unknowns. I need two of these equations. So the first equation says R3, make this smaller. So tooth equation. First one says R2 plus small r3 plus capital R3 equals R4. That's what we did. And the second equation, well, we didn't use 5 at all. So instead of starting from 2, let's start from 5. So that means that R5 gets me here. If I add capital R3, gets me here. If I add another capital R3, gets me to R4. Agreed? So the equation is R5 plus 2R3 equals R4. R5 plus 2 capital R3, because it's the large gear of 3, equals R4. All right? These are two equations, but my unknowns are T2 and T4. So they are inside the radii. I must explicitate them. I don't know the module, so I don't know these radii, but I know the number of teeth. So let's make use of the module. Let's use m equals twice r divided by t. So that means that r is mt divided by 2. And so I can say that mt2 divided by 2 plus m small t3 divided by 2 plus m capital T3 divided by 2 equals mt4 divided by 2. M divided by 2 goes away. And so I can turn this into T2 plus T3 plus capital T3 equals T4. T5 plus twice capital T3 equals T4. And so that means that T2 is T4 minus T3 minus capital T3, which is equal to T4 I don't have, so let's find T4 from equation 2 first. T4 here is T5 plus 2 capital T3, which is 60, twice this, which is 60 plus 40, which is 100 teeth. And so we have 100 minus 25, 75, minus 30 is 45. Of course, they must all be integer numbers. Otherwise, it doesn't make sense. You can't have 5 teeth and a half. Okay. Okay, all clear so far? All clear? That's because now we are introducing a method which is called the superposition method or the tabular method. It's the same thing, we just do it in a table, to solve the kinematics of this mechanism, which is quite complicated, but we can break it into simpler steps. So the tabular method works in this way. Let me get rid of these. The tabular method. You always have 3 rows and as many columns as you have bodies. How many bodies we have here? 2, 3, 4, 5, 6. Okay, so it's 5 bodies. So in this case, you have 3 rows, 5 columns. So you have row 1, and then you have body 2, body 3, body 4, body 5, and body 6. There you go. That's all you have. Let me take these here. And as I said, we only have 3 rows. Let me color code these. So we have 3, we said is green. 4, we said is yellow. 5, we said is red. And 6, we said is orange. Okay, we have identified these. This is the sun. This is the planet. This is the ring. This is another sun. And this is the arm. We also know that some of these are inputs, some of these are outputs, and some of these might be fixed. So we have that the output is 6. This is also the output. And the 2 is the sun, but it's also the input. And then what is fixed? It must be fixed, because otherwise it's either input or output. We only have one input, one output, so something else must be fixed. So let's check the question. Determine the speed and sense of rotation of the output shaft 6 if the annulus 4 is fixed. So the ring, also called annulus, is fixed. All right. Now that we have this information, what we want is what happens to the output when I rotate the input. That's the idea. I want to know the transmission ratio that I get at the output of this black box when I rotate the input. So the 3 operations are very easy. The first one is fix the carrier, fix the arm. What happens if you fix the arm?
Nothing revolves.
Well,
Just rotate.
yes, exactly. Nothing revolves, it just rotates. You are transforming an epicyclic gear train into a compound gear train. So there is no epicyclic anymore because you're fixing the arm. And that makes sense because what you want to do is split the complex kinematics into what happens when the arm is fixed versus rotating everything with the arm. Okay, so if you rotate the input once when the arm is fixed, you change the configuration of the thing. Then you rotate the arm, not just the arm, the entire box. 1 revolution, back, and see what happens. This is the compound motion. So the compound motion is split into operation 1, fix the arm. Fix the arm. What does it mean? Arm 0, doesn't rotate. Always arm 0. And rotate what is fixed by +1 revolution. What is fixed? Ring. Well, let's rotate the ring +1. Okay, let me not do this colored, otherwise it becomes a mess. Let me do this in blue. Always. So see, that's why it's very important to recognize the components and make sure that you know which one are the inputs, which one are the outputs, which one is fixed. Okay? Because if you don't do this, if you don't have this information here, you can't even start. Okay, now the question is, what happens? What happens to this gear when I rotate this? So what is the transmission ratio? Eta to 4. What happens to 2 when I rotate 4? What happens to 3 when I rotate 4? What happens to 5 when I rotate 4? This is what you have to put in these boxes. But now, this is a compound gear train. There is no epicyclic things. So we can make use of this. This we can use just this. That's it. Because everything was done with everything fixed here, so that works. So help me out. What is eta 24? Well, eta 24 is omega 2 divided by omega 4. Now, if these gears 2 and 4 are meshing, I can say that this is R4 divided by R2. Huh? Are they meshing or not? Let's check. 2 and 4, they don't mesh. Ouch. But if you follow the kinematic chain, they mesh via 3. They mesh through 3. That means I can say, okay, I can't say anything about this, but I can always say that this is omega 2 divided by omega 3 times omega 3 divided by omega 4. Do you agree it's the same thing? Just multiplied and divided by omega 3. But now these two are meshing, and these two are meshing. So now I can turn back into the transmission ratios of the single meshings and say, okay, 2 and 3. 2 and 3, it's 2 and small 3 that mesh. So omega 2 over omega 3, they are externally meshing. So it's minus T3 over T2. So this one is minus small t3 over t2. This is the first. Times the second one is omega 3 and omega 4. Let's check. 3 and 4, they do mesh. And there is the capital T3 that meshes with small t4, internally or externally? Internally. That means positive or negative? Positive. Okay, so omega 3 over omega 4 means the inverse, it's T4 over capital T3, because that's what's meshing. It's the larger gear that's meshing. And this is positive. Have you got a question? Yes.
Yeah, so how do you tell whether the gears are and whether the gears are internally or externally meshing?
You have to look. If it's a ring, it's always internally meshing. That's the idea. You have a ring. When you have a ring, it's always internally meshing. Yes.
How do you decide which one's meshing with which? How do you know that?
You look at the picture.
But yeah, but like you're saying, like T3 meshes with T2, how do you know it's that?
But this is 2, this is 3, and they make contact here.
How is it T3 over T2?
Oh, it's always the other way around. See, omega 1 over omega 2 is always R2 over R1. It's always T2 over T1. So the ratio of the omegas is always the inverse ratio of the teeth, because it comes from here. Omega 1 over omega 2 is always R2 over R1. Yes?
What's the difference between the big T and the small T?
You have here, the small t is this T3, and the large T is this one. So small t.
Why is there a big T there?
Because these gears are not the same. So this has 25 teeth, and this has 30 teeth. Okay. Okay, so if I now see if this wasn't, if this dumbbell was symmetrical, so this T3 and T3 could go away. But in this case, it's not symmetrical, so you must keep it as it is. So in total, eta 24 is equal to minus T3 T4 divided by T2 capital T3. And this one, I take it as it is and I shove it here. There you go. All right. So let me rewrite it down. Minus T2 T3 divided by T4. Is it? No, it's the other way around. Sorry. Let me copy this. This is what you need. Okay, now let's do eta 34. Eta 34, let's check. Eta 34 by definition is omega 3 over omega 4. Now if they mesh, easy. If they don't mesh, we have to see they mesh through which component. 3 and 4, do they mesh? Yes, they do. And we did this already. Let's have a look. Eta 3,4 is here. Omega 3 over omega 4 is here. So it's just this. I've done this already. So it's T4 over capital T3 with a positive sign. So this is T4. There you go. Easy. Let's have a look at omega 5, eta 5,4. Eta 5,4 is omega 5 over omega 4. Do they mesh together or not? They don't. But they do mesh via 3. So let's have 3. Let's multiply and divide everything by omega 3. Now, omega 3 over omega 4 is just this. We did this already. So the second one is given. T3, T4 over capital T3. And the second one is omega 5 over omega 3. They do mesh internally or externally? Externally. So positive or negative? Negative. So we are looking at omega 5 over omega 3. So it's capital T3 over T5, negative. And lo and behold, we can get rid of T3 now. So this is just negative T4 over T5. And I take it and I show it here. That's it. That's it. And that's it because the second operation is grab the entire gearbox and rotate it 1 revolution back. Because you know the ring must be fixed. We have just rotated the ring 1 revolution. In the end, this ring must not rotate. So what we do is rotate all -1. That means all. Grab the entire gearbox, rotate it -1. -1, -1, -1, -1, -1. Let me check the chat because it's flashing. Only the ring meshes internally. Yes, only the ring meshes internally. How do we know if it's external or internal? Well, it's 90% of the time will be external meshing. When you have a ring involved, it will be internally meshing. Yes, Mahmoud is correct. Ring gear connections are always internal. Great. So what's the third operation? I told you we have split the motion, the kinematics into 2. So that means now we have to do, it's called a superposition method. That means we have to sum everything. Sum. And so that means that now this represents eta to 1. What is 1? Look, we didn't use 1 anywhere. What is 1? What is 1? In the picture, what is 1? It's the ground. So that means omega 1 is always 0. The ground doesn't rotate. That's the idea. This is the fixed. So what I'm saying here, this is the absolute, this is the transmission ratio, the absolute rotation of omega 2 with respect to the ground. Okay? So let's call this omega 2, and that's it, omega 2, 1. And so this is negative 1 plus T3, T4 divided by T2, capital T3. And so this is omega 3, 1. And so this is T4 over T3 minus 1. And this is 0. There you go. In the absolute motion, the ring is fixed, doesn't rotate. And it makes sense because the ring was fixed in the first place. So this is a sanity check. This is minus 1 plus T4 over T5. and this is -1. So this is omega 3, 1, this is omega 4, 1, which of course is 0, omega 5, 1, and omega 6, 1. Now the question is asking the speed and sense of rotation of the output shaft if the input shaft goes 200 RPM. So if omega 2 is 200 RPM, how much is omega 6? Okay? Well, now we can find the transmission ratio, omega 2 over omega 6. This is the input, this is the output. Omega 2 over omega 6 is this beast minus 1 plus T3, T4 divided by T2 capital T3 divided by -1. This is numerator, denominator. And so this gives a number. That number is, guys, can you do this calculation for me, please? This is 1 plus T3, T4 divided by T2 capital T3. Can you do this for me? As you can see, this has no units. No units because it's a ratio. I'll do this myself. So T2, no, complicated. T3 times T4, that's
Which
for, we were looking at this one. This one. Can you do this?
-77
Guys, I got two completely different numbers. So it's -77 over. Can you give me a decimal number? -2.85.
Plus 2.85.
Well, it's plus because this is divided by -1. So plus 2.85. Okay, so that means the ratio of omega 2, the ratio of the input over output is 2.85. That means the output is input divided by 285. So let me go here. Let me grab these and put them down. Then I'll give you a break. Don't worry. So that means that omega 6, 1, which is the output omega, is omega 2, 1 over 2.85. And so that means since omega 2, 1 is 200 RPM, 200 RPM divided by 2.85 gives me 200 divided by 2.85 gives me 70.17 RPM. Okay? So the input shaft rotates at 200, the output shaft rotates at 70.17. In the same direction or in the opposite direction? Since it's positive, it's a positive ratio, that means they rotate in the same direction. But did it work? Yes, it did. Okay, I'm shocked. You did the correct calculation. All right, guys, as you can see, it's not hard. You just have to be mindful of some things, especially recognize all the bodies. Be mindful if they are externally or internally meshing, and make sure that you have the correct ratios. I'll give you 5 minutes break, and then we'll resume with question 2, which is very easy also. Okay. Yes. Of course, this one. Lynn, have you got any questions? Any particular thing online?
No, I think you all answered the tricky ones. Another, there's students ask for the gear and the torque relation. I think next section maybe just
Yes,
start
yes.
with
So in
the
the next-
second one.
In the this is just kinematics so far. In the next section, we do the kinetics and we'll talk about the free body diagrams and the forces and the torques.
But the question 2 are very similar to question 1. So maybe just directly go to the kinetic parts.
Oh, I think it's the same actually. Isn't it the same?
Yeah, they were quite similar.
Oh, now it says just the wheel 5 is fixed.
Okay, but I mean,
Because we'll probably skip this one. I will just start the question and then I'll let the student solve it because it's very similar to what we did already.
Because they prefer your recap. I think maybe next
Yes,
section
yes.
just start from
I'll do
recap.
this one. This one. I'll do 3 because it's a different figure and it's got a different kinetic gears.
But do you still have time for the next section? Because next section you have question 3 and 4.
Oh, well, it's fine. But this is, yeah, okay. This is next section anyway. Start the next section. So it's good.
Okay, yeah, that's fine.
Dr. Faris mentioned the bicyclic gears not having moments as all the shafts are concentric. But how could you have moments in standard gear train if everything is free to rotate? Well, they are free to rotate, but they transmit moment because the shafts are flexible. That's the idea. Okay, so if you are rotating at different speeds, you know, it's all about power. It's going to be clearer now that we attempt question 3. I'm going to explain that stuff as well. Don't worry. Yeah.
Do you know how you were talking about the left side, where it says reason R5 plus R3 and then add R3 again? Did you add R3 from the left side, but not the right side?
Yeah. I mean, if you add it from the left side, you don't get to R4. You are slightly shorter.
So R5
Yeah.
plus R3, R2 plus R3 equals R4.
Why? How? Yeah. But they're not the same. So if you do R5 plus R3, you get to the middle of the shaft 6. Because if you start from 2, the only way to get to the middle of the shaft is smaller 3. I'll show you. Look here. R2, if you add the small R3, you get here in the middle. If you add the large R3, you get here. Which is, and so what do you add now to get to R4? You can't add R3 because you end up here. You must end where the tooth of 4 is. Okay, so the only way is to follow this until you get to the middle of this, and then you hop onto the other gear and go up. In the next equation, instead of starting from here, you start from here. Then you have R5. Then you want to get to the middle of the shaft, so it's R3. And then it's another R3 again. Okay?
Arnaldo,
Yes.
how come if they're all if all the gears are different ratios, how come you can turn it all one time?
You take the entire gearbox without rotating anything, and you rotate the gearbox. It's an imaginary thing. You're not actually doing it. You're just splitting the kinematics into a compound gear train by fixing the arm and rotating everything. Okay, and then since the ring must be fixed, you take the entire thing and you rotate the ring back so that it was as if it was fixed. Okay. Yep. Again? Because we need to know, we don't know all the number of teeth. So we are missing T2 and T4. So we want to find some relationship. Since the teeth and radii are related via M, so if you get a relationship on the radii, then you get a relationship on the teeth. Exactly. Okay, guys, I think it's time we resume. Now this is question 2. I don't want to solve question 2. And I don't want to solve question 2, not because I'm scared of it, but because it's very easy. It's the same figure, it's the same thing. The only thing that changes now, instead of fixing the ring, we are fixing one of the suns. So instead of fixing the ring 4, we are fixing the sun 5. And we are letting the annulus 4 free to rotate. So the input shaft is still 2, but now the output is 4. The output is the ring. So that means you do exactly the same thing, take exactly the same table. But now you have to change this. Oh, you're right. Thank you. So I just copied and pasted the same table down here. But now the ring is not fixed anymore. Now the ring is out. And the arm is nothing. And this sun is fixed. So how does this change the table? Well, you have to get rid of these. And these, and these, and these, and these. And now the only thing that changes really is these etas. What happens to 2? So the fix is 5. Fix the arm and rotate what was fixed. Rotate what was fixed. Now what was fixed is this. So you get 0 here. But now these etas now must change to eta 2, 5, eta 3, 5, eta 4, 5. Okay? So just what happens to 2 when I rotate 5, what happens to 3 when I rotate 5, what happens to 4 when I rotate 5. Again, it's the same thing. You can do this at home, very easy. And this is -1. Okay? Nice, that's it. You do exactly the same thing. Now let's do question 3. Question 3, we have figure 2, which I believe is this one. Yep, this one. I have here. Depicts an epicyclic gear train. together with the line diagram representation, all gear wheels have the same module. Power is supplied to shaft 5 and is taken from shaft 2. Shaft 5 rotates at this 300 radians per second, and the ring 4 is fixed. Again, determine speed and sense of rotation of the output shaft. We don't have all teeth, so we must write a teeth equation here. Also determine the fixing couple which must be applied to the ring so that the power transmitted can be 13,000 watts. So let's do this. This is the picture of question 3. So help me out. Which one is the sun? So let's start with the numbers. 2, 3, 4, 5. What is 2? Correct. Arm. What is 3? Planet. How many gears we have on the planet? Correct. What is 4? Correct. What is 5? Correct. All right, very good. So let's write the teeth equation. What's the relationship? Well, let's start from here. This is the baseline always, the center of the mechanism. So if I go up by R5, the radius of 5 gets me here. And if I go up by the radius of 3, it gets me to the middle of the arm. If I go up by the radius of 3 one more time, it gets me to the radius of 4. Do you agree with me? This is what's happening. So R4 is R5 plus 2R3. Agreed? Agreed. That's the only equation we can write. So teeth equation we have that R4 is R5 plus twice R3. That also means since they have the same module, T4 is T5 plus 2T3. Agreed? Agreed. So how much is T4? Let me check. No, T4 is given and T5 is given, so we don't know T3. So T3, let me rearrange this equation. T3 is T4 minus T5 divided by 2. Is equal to 60 minus 30 divided by 2 is 15. Very good. Right? Good. Now, what else? Well, superposition method. Which one is fixed? Which one is input? Which one is output? Help me out. Which one is the input? 2. Which one is the output? Which one is fixed? Okay, good. The planet can never be fixed. Doesn't make any sense for a planet to be fixed, otherwise it's not an epicyclic gear train. Okay, and the planet cannot be input or output because it's inside the machine. Okay, you can't make it output or input. The planet can only be a planet. So how many rows we have in the table? Always 3 rows, because there are 3 operations. How many columns? 4. So I have, let me copy and paste this, come on. There you go. I just have to change things around. So let me get rid of these and these and these and these. Okay. So we said 2 is the arm. 2 is the arm and it's in. Then we said that 3 is the planet. Then we said that 4 is the ring and it's fixed. Then we have the 5, the sun, and it's the output. And there you go. I don't need this. Don't need these. There you go. Very easy. Now, the ring is fixed. So I rotate the ring 1 revolution while keeping the arm fixed. So the arm is fixed, 0. And I rotate what was fixed by 1. And now, what do I put here? Eta? Eta? Chat? Eta? Which number? 3-1? Do you agree? 3-2? Looks like a lottery. 3-3? Yeah, of course. 3-4. So what do you think? What happens to 3 when what am I rotating here? I am rotating 4. So I want to see what happens to 3 when I rotate 4. Eta 3-4. So this means this is eta 5-4. Okay, don't be fooled. It depends on what you are rotating and what you are observing. This is the column 3. So we are observing what's happening to 3 when I rotate 4. And this is what's happening to 5 when I rotate 4. Okay, so how much is eta 3-4? Do 3 and 4 mesh together? Yes. Yes. Internally or externally? Internally. That means positive or negative? Nice. So eta 3-4, let me do it here on the side. Eta 3-4 is omega 3. Again, I am doing this step by step. When you get skilled enough, you can just write it down as it is. This is T4 over T3. Positive because it's internally meshing. That's it. You don't need to do anything. This is T4 over T3. Eta 5-4. Do they mesh together? No, they don't. But they do mesh via 3. So I can multiply and divide by 3. And then 5 and 3 mesh together. Yes, they do. Internally or externally? Externally meshing. So that means negative. So this is equal to T3, so negative T3 over T5 times T4 over T3. I know this because it's here. This one is this one, T4 over T3. This also means that T3 and T3 can go away. And so in the end, I get that eta 5-4 is minus T4 over T5.
Can you minimize the chat?
Again?
Can you minimize the chat?
Oh, yes, sorry. There you go. All right. And there you go. So the second step is always the same. You take the entire thing and rotate it -1. And the last step is, this is -1, this is 0. Makes sense because +1 -1, ring is fixed. And this is T4 divided by T3 -1. And this is -1 plus T4 over T5. Okay, which one is the input? Which one is the output? This is the input. This is the output. So this over this. So eta 1, 5. Sorry, eta 2, 5 is omega 2, 1 over omega 5, 1, which is this over this is 1 over 1 plus T4 over T5. How much is this? Guys, help me out. Calculations. How much is 1 plus T4 over TT5 to the power of -1? I got someone in the chat. 1 plus T4 over T5. No, it's not T4 over T5. Can I get a number? Chat, a number here? Sorry, say again. It can't be negative.
The negative sign at the bottom.
Yeah, no, there's no negative. Well, I mean, it should be negative and negative. Okay, so I'm not going to put it. So how much is this? Come on. How much is this? Come on. A third? I'm trusting you. Second? Input over output. So it's 2 over 5. Output is 5. Out. Shaft 5 rotates. So, power is supplied to shaft 5 and taken from shaft 2. Guys, I was trusting you. Luckily, this doesn't change anything. We just have to invert the ratio. Okay, so this is, guys, I was asking you without looking, and I should have not trusted you. This is the input, and this is the output. So this means we have to invert this -1. That's the idea, okay? So what we have is omega 5,2, so eta 5,2 equals omega 5 over omega 2, which is 1 plus T4 over T5, which is equal to, is it 3 now? So T4 over T5 is, it's 3, yes. So this is 3. All right, this is 3. And what do we know now? We know that omega, where is this? Omega 5 is 300 radians per second. So omega 5 is 300 radians per second. So that means that omega 2, this is omega 5, 1, omega 2, 1. So omega 2, 1 is omega 5, 1 divided by 3. Which is equal to 100 radians per second. In the same direction or in the opposite direction of 5? Same. They have the same sign. So they are going in the same direction. Nice. Now, what do we have now? What do we have now is this. Determine the fixing couple which must be applied to the annulus 4 if the power transmitted is this much. Now let's have a look at what's going on here. Let's have a look at this. 2 is the input, no, 2 is the output. So power goes inside here. Power in. I'm using W dot, which is the rate of work. What is power? Energy in time. What is work? Work is energy. So the rate of work is power. So the rate of work in, and then we have a rate of work out. what is power? Energy in time, we said, but also
4 times.
is force times speed. Now this is a rotational system. So the equivalent, the rotational equivalent of force is torque. The rotational equivalent of speed is angular speed. So W dot is also torque times omega. So let's put a few definitions here in. Power. Power, W dot, is torque times omega. For torque, I'm not using T because we have too many T's already. Number of teeth, small t, capital T. So let's not get confused. Let's use L for torque. Okay, so again, don't get confused over just symbols. These are just, this is Newton meters. This is radians per second. And so this is equal to watts. Okay, watts is joules per second. All right, what is joules? Joules is also Newton meters. Force times distance. Okay, this is the first equation. Equation 1 is definition of power. Then we have balance of power. If the system is not accelerating, whatever power I put in goes out. So at constant speed, whatever power goes in, power flows out. Again, this is assuming 100% efficiency. Because if you have efficiency, you must have a coefficient here somewhere. Okay?
Shouldn't that be minus?
It's that, well, it's this is this. What I'm saying is that this is the same as W out. The other equation you might want to write is this. That's exactly the same equation. Well, yeah, let's write it in this way. So you might be more familiar with this. Okay, that's the idea. Now, when you are inputting power, the torque is always in the same direction of the speed. That's what means giving power. I apply a torque and the shaft follows my torque. If you are extracting power, the shaft wants to resist the torque. Okay, so the angular speed you get is the opposite the direction of the torque you provide. Okay? Have you got a question?
Is that why it's minus?
Yes, that's why it's minus.
To the talk.
Yes.
Say it again, sorry.
So when you are providing power,
Yeah.
the torque you are giving goes in the same direction as the speed.
Okay.
When you are collecting power, okay, the speed goes in the opposite direction of the torque. Because you are providing energy here and there is a resisting torque on the other side.
Okay.
That tends because you have Newton's first law that says I don't want to accelerate. Okay?
Okay.
So it's always resisting on the other side. So the power in is the same number as the power out, but it's the opposite sign. Because L and W, this is what I'm saying, if they have the same sign, this is power in, and even if they have the same negative sign, it's also power in. If one is positive, the other is negative, it's power out. Last thing, last equation that you need is the Newton's second law. The sum of moments, the sum of torques must be 0. Why 0? Because we are going at constant speed. We are not accelerating. If we are accelerating the system, the sum of torques is I alpha. Remember, so it depends on how large is the gear because you have to accelerate a large mass, so it must take time. Let's say we are at steady state. Steady state, we have constant speed, and so the sum of torques is equal to 0. Newton's second law says sum of torques must be 0. Now, let's look at, these are the sum of the external torques. Why not the internal torques? Because if it's an internal torque, there are two that are equal and opposite to each other, because that's for Newton's third law. So we just take into account the external torques that are here. What are the external torques? Well, the input torque, the output torque, and the fixing torque. That's all there is. If I don't provide a fixing torque here, if I have input and output and I don't fix 4, what happens is that 4 will rotate, and then I don't get the same ratio, gear ratio, because I have 1 input and 2 outputs at this point. Okay, good. So in order to make 4 not rotate, since it wants to rotate, and I don't want it to rotate, I must provide a torque that makes sure that it gets fixed in place.
You know how you can change which ones are fixed and which ones are not?
Second, how do you change?
Yeah, like
Well, there are various mechanisms, but you can do it electronically. Okay, you know, at some point you fix one, release the other. You can do this quite easily.
you could probably like have something in there that measures the amount of ratio, like, you know,
Yes, and you can do this electronically, but you can do this mechanically if you have a governor. Okay,
yeah.
so do you know that mechanism that goes like this? Something like this. So this is pinned,
Oh, yeah.
and this is pinned, and so this has mass, this has mass. So this rotates omega, and if this omega is large enough, these go apart, okay, and this goes down, and so you can activate a mechanism in this way. This is a governor. This is what you use in old steam trains, old steam locomotives, and they use that to regulate the the inflow of steam to the chamber. Okay. All right, so let's go here. So these are the 3 equations that you need. You don't need anything else. This, and this. Okay, so let's solve the problem here. Let's solve this problem by saying that the power input is 13.5 kilowatts. That's wrong units. Okay. 13,500 watts, which is equal to W dot in. What is the input torque? So the torque at the input shaft. What's the input shaft? 5 L5 times the omega 5 times omega 5. All right, this is the first equation. The second equation is W out. W out is negative 13,500, which is equal to L4, sorry, not L4, what's out 2, is equal to L2 times omega 2. Because 5 is the input and 2 is the output. So this is equation 1, this is equation 2, and we have used the definition of power. We have used the definition of power and the balance of power, because we are saying that these are the same. Okay. And finally, we use the Newton's second law by saying that L5, L in, let's do this, L in plus L out plus L fix must be equal to 0. but L in is L5, L out is L2, L fix is L4 equal to 0. So that means that L4 is minus L5 minus L2. Can you do this calculation for me? First of all, with this equation, we find L5. With this equation, we find L2. And with the last equation, we find L4. Okay, because this is a number. This is a number. Omega 5 is also a number, 300. Omega 2 is also a number, 100. Okay, so help me out. How much is L5? L5 is rate of power. So power in divided by omega 5. And how many Newton meters is this? Second? 45. And omega L2 is power out divided by omega 5, omega 2, sorry. Power out is negative, so let's put a negative sign here. How much is this? 135. So minus 135. It must be because omega 2 is positive. Omega 2 is positive. So the torque must be negative. And so that means that on L4 is minus 45 plus 135, which is minus 45 plus 135 is, second? Sorry, how much is that? 90 Newton meters. There you go. So you need a torque of 90 Newton meters. There you go, plus 19 Newton meters to make sure that the ring is fixed. What's the matter?
Is there a minus before W out?
Yes.
Does that not make it plus?
Well, you're correct. You're right. Sorry. So this, I was just pointing out that this is negative, but
Yeah.
W out is negative already. So yes, you don't need this. You're right. Thank you. All right. How bad is this? Not too bad. Okay. After all, it's always the same thing. And if you practice, you get it very easily. The last thing I want to show you before we go home is the free body diagram of a gear that is rotating. Because some questions, like question 5, asks you, if there are 3 sets of planet wheels, what's the magnitude of the forces, the tangential forces, that are being exchanged in the teeth? Because these teeth exchange forces. And they are tangential to the pitch circumferences. So what's the magnitude of this force? Well, you do. Let's have a look at this. I'll draw this one. Sorry, you can't see it. I'll draw this one in front. I mean, I'll draw the front. So let me delete this one. We don't need it. I'll draw the front version of this. So we have a ring, sorry, a sun. Then we have a planet. And then we have a ring. Okay, so this is what you have. In reality, we have 3 planets, it says. It says we have 3 of these. Nope. One here and one here. So that means we must make this a bit larger. More or less. Okay. So that's why the carrier arm is called a spider, because it looks like this. All right. This is the spider. That's why you can turn it. You can apply a torque to that spider, so everything turns around. And what's the free body diagram of these gears? Let's do the free body diagram of the sun gear. The sun gear is, we said that the sun gear is the input. Is it the input? Well, no, let's do the, what was the input? I can't remember anymore. No, the input is, yes, the input is the sun gear. So that means if I do the free body diagram of this gear only, that means just this devoid of all the other bodies around it. This only exchanges forces with the 3 planets, so that there are 3 forces around it, but also there is a torque on it. L5, remember L5? L5 is a torque. So we have this is omega 5, and then we have L5, which is in the same direction of omega 5. And since this must be in equilibrium, the 3 tangential forces must be rotating in the opposite direction of L5, because the sum of all these must be 0. So if this goes in this direction, oops, this goes in this direction, that means that the forces must be this one, F5, 3. So this is 5, remember this is 3, the planet. This is F5, 3, because it's the same planet, just another set of the same thing. And this is F5, 3. Do you agree with me? So the sum of moments is equal to 0. Agreed? Because it goes at constant angular velocity. And so we have, this is already a moment. So minus L5. I say minus because it's, because I used, let's say that the positive direction is this. No, let me change all these directions, please. Because otherwise we have the convention that positive is this, okay? So let's use this as positive. L5, so this is F5, 3, this is F5, 3, this is F5, 3. All right? So this is the sum of moments equal to 0. And so that means that L5, positive, counterclockwise, minus F5, 3 times the radius of 5. Agreed? Force times distance. Force times perpendicular distance. And the perpendicular distance is always the radius of 5. Agreed? So that means minus F5, 3 times R5, minus F5, 3 times R5, minus F5, 3 times R5. So I'm saying minus 3 times equal to 0. All right? So how much is the force? Well, F5, 3 is L5 divided by 3 R5. There you go. All right? This is how you find it. L5 you found earlier. L5 is 45 Newton meters. R5 you can find only if you know the modulus, because you know that 5 has a certain number of teeth, but you don't know the radius of 5. Agreed? So R5 you must also find by modulus times the number of teeth of 5 divided by 2. Okay. So let me check this. Yeah, see, when they ask you for the force, they always give you the modulus, because otherwise you have no idea what's the radius. They must give you modulus. Okay, let's do the free body diagram of the planet. If I do the free body diagram of a planet, say the planet at the top, how many forces are acting on the planet? Is there a torque on the planet or not?
Yes. So the top.
It's an internal torque. So that means you have 2 torques. they are equal and opposite to each other, so you can disregard them because one comes from the planet and one comes from the ring. So one comes from the sun, one comes from the ring. Okay, there are exchange forces, of course. There are exchange forces because this exchange changes a force with the ring. So let's say this is rotating in this direction. This exchanges a force with the ring, F3, 4. This exchanges a force with the F3, 5. Exchanges a force with the sun. Are these balanced? There must be, sorry, they must be in the same direction, because otherwise they are not balanced. I mean, in moment. Okay? The problem is, these are in the same direction. So that means the sum of these forces is non-zero. So what's going on here? What's missing? The force from the carrier arm. There is a force. Okay, from the carrier arm. Okay? Now the sum of forces is 0. All right? Okay. Make sure that you know what you're doing. What is the free body diagram of the carrier arm? Well, that's very easy. You take this. Free body diagram of the carrier arm is all forces, and of course there is a torque here. So these all go in this direction, so the torque goes in this direction. Okay, so everything is in equilibrium always. All right. So as you can see, it's nothing different from what we did in first year, although it's applied to a complicated system. But it's always free body diagrams, always forces, always kinematics. Now this is entirely rotational problem. That's it. Okay. Thank you very much, guys. I'm going to stop the recording.